Hi everyone. Thank you so much for joining us today. I think let's wait a few more seconds so everyone's entering the meeting. Yeah, I think we'll get going now because we don't want to go over everyone's lunch break. So, hi everyone, and thank you so much for joining today for IStructE Essays Technical Talk number 6 for the year. I'd like to give a warm welcome to Peter Debney, who will be speaking to us today on computational engineering. Who better to be providing this talk than Peter Debney, author of the recently published IStructE Guide on Computational Engineering. In addition to working as a civil engineer, Peter has worked directly in the engineering software industry, helping develop the CAD programs XSteel for Tekla Structure and 3D Plus, as well as the Finite Element Analysis and Design program, GSA. Without further ado, I'll hand over to Peter Debney. Thank you so much.
Okay, so thank you, Fiona. Yes, thank you. Thank you for the introduction. Yeah, I'm Peter Debney. I wrote Computational Engineering. So today we're going to have an exploration of the book, how I came to write it, and maybe more importantly, what it contains. So yeah, me, introduction to me, personally speaking, I've always loved making models, Lego, Airfix, discovered computers as a teenager. I don't know how many people remember these particular computers, but these were the first ones that I played with and often broke, but we won't go into that. And because I love buildings, not just Lego ones, I then went to University of Surrey, studied civil engineering, and then I've worked at a variety of companies, initially as a structural engineer with a specialism in computing, and then in computing with a specialism in structural engineering. I joined Arup 20 years ago this year, and joined the Oasis group, which is over Arup Systems at Arup Software, about 16 years ago. Working mostly in the structural, but these days also run the support team, the quality management system, and so on. Okay, all right. So the book itself, as I really wanted a book that was. I wanted a book that explained the broad sweeps of computing for structural engineers, sort of equivalent to J. Gordon's Structures or Why Things That Don't Fall Down. Yeah, and if you haven't read that book, read it. It's absolutely brilliant. Love it. It got me through my degree, that one. Anyway, so I wanted a book that explained what and why of computing for engineering, not just a list of formulas. So I did put some useful ones in the back, and because that book didn't exist, I realised that I was going to have to write it. So it encompasses about 35 years of experience in engineering and computing, mostly aimed at graduates, but it's also been picked up by a lot of senior engineers wanting to deepen their knowledge, and also by some of those more senior still wanting to know what the youngsters are talking about. Now, most engineering books are like car manuals that tell you how the engine works, and once you know the mechanics, you're then expected to take the keys and drive off. Whereas computational engineering is more of a driver's manual, explaining what you need to know as a practicing engineer. And so it covers why we use computers when designing, but also design methodologies as well. It touches on parametrics, quite a large section on finite element analysis, goes into optimization of structures, and then finishes with a look into the future of structural engineering, artificial intelligence, machine learning, digital fabrication, cloud, quantum, and some thoughts on the future role of engineers. And there's some appendices as well, with some useful bits and pieces. So why use computers to do engineering? Well, the main reason is because they are very, very good at doing maths, far faster than we can. They'll do that without error, if programmed correctly, without tiring, apart from possibly overheating, and without getting bored of mind-numbing tasks. Because despite names like artificial intelligence, they actually have no minds whatsoever. They just get on with it. Computers can do our drudge work, freeing us up to do all the interesting things. Yeah, the creative, the imaginative, the interpreting, the communicating, and the human. So design, first of all. So one of my personal bugbears is the confusion over the dual meaning of the word design. One meaning, understanding and interpreting the client's brief and needs, working with the architects and other consultants to determine the best approach, the form, the layout, and the methodology to meet those needs, or calculate the beam sizes and rebar quantities. Now, option 1 is creative. Number 2 is mechanical. Though still crucial. The devil is in the detail, and we must never forget things like the Hyatt Regency Hotel. So now, I know some people specialize in the details, and we love you, that they are very important, and you guys always impress me with the depth of knowledge, and we need that knowledge to keep it safe. On the other hand, in the book, I'm looking at the scheme rather than the detail aspect of design. So how do we go about designing? Well, not on a blank sheet of paper like this, but with requirements, constraints, and options. Now, the requirements and constraints speak for themselves, but the options, I think they're the interesting part. So every year, in the IStructE chartership examiners complain that candidates struggle to find two distinct solutions to exam problems. We know the options. Any scheme, we know the options. It's a brace steel frame or a moment concrete frame. Well, maybe not. I mean, certainly the students I've taught at local universities know that two options are always a truss or a portal frame, which is a similar problem itself. But in engineering, we talk about creativity, not enough in my opinion, but it's in the options that creativity is most found. And it's said that if all you have is a hammer, all problems look like a nail. Now, when I was preparing for my chartership exam more years ago than I'll care to mention at the moment, I decided to create an exhaustive list of all the possible ways of crossing a horizontal gap, and likewise to keep a load at height. I mean, I never did finish because there were far too many options, possibly an infinite number, but certainly a very large number. There is no excuse for just two options. So for me, creativity comes from knowing what options there are and then choosing the best options. Now, how we go about implementing that. So Hermann von Helmholtz and Henry Poincaré put it more succinctly. So creativity comes from saturation, learning everything, especially about the subject, but also everything else. As engineers, we can learn so much from natural structures such as skeletons and muscles, shells and trees. We can learn from art, from maths and science, from everything. Then there's the incubation, thinking about the problem, sleeping on it. This part can take time. There's illumination. You get an idea. Now, Murray Gell-Mann got his Nobel-winning quantum breakthrough by making a mistake in a lecture. But without the saturation and incubation periods, he would never have realized the error was the answer he was looking for. And then finally, validation. You have your scheme, your approximate sizes, but you now need to do the analysis and details to ensure that it will work, as well as exploring how to make it better. Okay. Now, the Design Council puts design another way. See earlier about there being more than one way to do something, and they introduced us with the design double diamond, where the project you start from the left and work away across the right. And you note that in the discovery and development phases, the design broadens when you explore the options, what they can be. So don't close these options down too soon. Whereas it's in the define and delivery phases that you need to refine and concentrate what the problem is and what is your solution. And even this doesn't take into account the cyclical nature of design. So to help with that, I want to take a little closer look at the development phase and the method we call parametric design. Now, we all know that layouts are driven by constraints. dimensions. We know it too well when the architectural client changes them, making the scheme bigger or smaller and so on, then we have to start all over again. And with parametric design, we plan for the change by encapsulating those constraints and rules into a geometric computer model, which is a design led by parameters. And this might be mundane things like the span of a decking slab, or it might be complex like the offset from a curved spline surface. The parametric design started in the aeronautical industry, and I think the first significant parametric design in the building industry was Frank Gehry's Guggenheim Museum in Bilbao, in Spain, which opened back in 1997. Now, parametric design in the 90s was on supercomputers running software designed for making fighter jets. Today, it's much simpler programs like Rhino, you see here, running a plate of spaghetti script in Grasshopper to generate the geometry, and then exporting the Iffy analysis, export to Iffy for analysis and CAD for detailing and documentation. Now, BIM, building information modeling, used to be all about neutral file formats, but today we've moved on. Now it's all about digital workflows, though the underlying principle of data reuse remains the same. Now, you've got the design, you need to validate the design, usually using finite element analysis. Now, Iffy was first used in the 1950s, aircraft again, and in the 1960s on buildings. Now, as far as I know, the first structural engineering use was by Arup on the Sydney Opera House, though I'll be very interested to know if you know of any earlier examples. Now, FE books, as you know, they tend to focus on the maths of the methods, which is great if you want to write your own program, but the majority of engineers just want to use a commercial program. So my aim here was to teach how to make the best models with a little bit of maths thrown in, as it can be interesting and can be informative. And as a side, I think FE universities, FE the maths tend to be taught more at universities because marking maths is a lot easier than modelling. Modelling is an art, and therefore there is no one right way of doing it. Rather, better ways and worse ways, on an occasionally completely wrong way of doing it, of course. So, what is a model? Models are not reality. So this is not a real beam. These are not real connections. They are a simplified representation of reality. So the model doesn't represent everything about the real connection, the real beam, but they are close enough for engineering. So the model is a simplification of reality, it's not reality, and therefore it's important to remember that all models are wrong, but some models are useful. Is it possible to do a totally realistic model and test it with everything the real structural experience over its service life? No. The closest you can get is to build the structure for real out of steel and concrete, then load it until it breaks, then repeat with other loadings. But would that be 100% accurate? Well, no, that won't be either. Due to tolerances, the steel and concrete sections will be slightly different size. The frame won't be quite as plumb. The wind, snow, and earthquake loads will not be exactly the same. Besides which, we don't know exactly what the structure will experience over the next 50 years. It's just not possible. As I said, the art of engineering is to get answers which are close enough. To illustrate this, let's consider the stool paradox. Now, if you sit centrally on a three-legged stool, then your weight will be carried, approximately, equally down each leg. The design load on each leg is your weight divided by 3. But if you sit on a four-legged stool, then will the design load be divided by 4? No, because the stool will not be perfectly built, the floor it sits on won't be perfectly flat, and only 2, possibly 3 legs will actually be fully in contact with the floor. Your weight will be mostly carried by 2 of the legs. meaning that design load is now your weight divided by 2, an increase of 50% thanks to the addition of an extra leg. Now, when we build analysis models, we tend to assume the structure will be perfect, the floor is smooth, the stool is even, every leg is fully in contact with the floor. Reality is not so neat. Structures will often work the way we design them, so if they have enough ductility. In the case of the stool, the connections may have a little bit of flexibility if they're not glued, the top may warp a bit, and so on. Now, our building structures often have similar problems. University, we tend to study statically determinate structures, so pin supports are fine. If a footing moves, they make very little difference to the structure. We have an indeterminate structure, multi-span beam, a frame, a raft, then suddenly the support stiffness becomes crucial and you can get rubbish results like I'm showing here. Interesting enough, this was a reproduction of a mistake that I did make myself many years ago. So some moment redistribution occurs because of plasticity, but a lot will occur because not because of the error in assuming that support is infinitely stiff. Model the ground with springs, or support with springs, and you'll notice the sagging increases, hogging reduces, and so on. And likewise, the retaining wall model I did back there would also give correct bending moments in the base. Now, do we really know how stiff the beam will be? How stiff the ground? Approximately. How confident can we be with the results? Well, take a steel beam. When rolled to European tolerance standards, I'm sure South African standards are similar, its area can vary by about 4% and its bending stiffness by about 10%. This means that every factory-made beam, there is no point calculating deflections beyond 2 significant places, or 2 single figures. Concrete beam stiffnesses will vary even more, both from the tolerances, effects of cracking, and so on. Now, FE models are analogues of the real structure. And we model them with 1D, 2D, and sometimes 3D elements. Now, 1D elements are great when the stress flows are essentially one-dimensional, like in beams. The one dimension, the length, is considerably more than the other two. 2D elements are suitable when the stresses move in 2 directions. One dimension, thickness, being considerably less than the other two. And 3D elements, well, I need to guess about that. And now, these are all analogies, and these analogies will break down when the stress flow directions change, like at the connections between the beam or slab and the column. And for this reason, there's an simple overall model can inform a more detailed model of a part of the structure, but you would not want to model the entire structure in such detail. You would not want to model either of these two examples totally in 3D elements. It would be a complete waste of time. So what does make a good model? It needs to be as accurate as necessary. Do a sensitivity check, vary the stiffnesses, the dimensions, do a p-delta or a non-linear analysis. Are the results close enough? It needs to be as realistic as appropriate. Remember that increased realism is subject to diminishing returns. Stop when it's not worth continuing. It needs to be as simple as possible. Simplicity, this comes from experience. My first FE model back in university took 24 hours to run on the university mainframe. Today, I would achieve the same results with perhaps a model with perhaps maybe only 1% of the number of elements in. It also needs to be useful and relevant. Does the model give you the answers you need? For example, static or dynamic analyses often require quite different models. So the essential question you need to ask yourself is, what is the question that I am trying to answer? Then make sure that you design your model to achieve that. Now, analysis methods. Now, it would not be a book looking at FE if it did not have some exploration of the maths behind the methods. Now, my requirement in the book was to do it with a minimum amount of maths. And now we've only got, let's say, 5 minutes to look at the topic, which normally takes up entire textbooks. So let's see if I can keep it both useful and simple. Now, in a simple beam, we know that when we apply a force to a structure, its deformation, U, is proportional to the external force, F, and inversely to the stiffness, or stiffness times deflection equals force. If you look at this beam element, which only has axial stiffness, keep it simple, you'll know it has some stiffness horizontally in the x direction, but 0 in the y direction. Now, there will be forces applied to both ends of the element, which can cause both ends to move. Again, keeping it simple and looking only at the forces and displacements in line with the elements, we can see there's U1, U2, N1, N2, and so on. And we can write these equations out in a matrix form, so that we can then use matrix maths to find all the displacements and all the forces. Now, we already know some of the forces. These are the externally applied forces. The other forces we're finding are the reactions. And also you find when you do the analysis, the forces within the structure all cancel out because it's in equilibrium, or at least close enough. So we have the stiffness of each individual element, or each element stiffness matrices, and we combine these together to make a global stiffness matrix. And for simplicity, I've shown them separately, but in reality they'll actually overlap and combine wherever they have a shared node. And for extra simplicity, we can write this as Ku equals F, so the stiffness matrix K times the displacement vector U equals the force vector F. Now, we need to find the displacements U, and but we can't divide by a matrix. Instead, we need to multiply by the inverse of the stiffness matrix on both sides. And now I'm not going to tell you how to invert the matrix, and besides, it's not important. But what we then get is the nodal displacements are equal to the inverse of the stiffness times the forces. And that, ignoring a whole host of details, is simply how FE analysis works. Simple. And from this we find the displacements. Displacements give us strains, strains give us stresses, and the stresses give us forces and moments. Everything derives from the nodal displacements. Now, in the book, I'll then build on from there. So P delta analysis, which includes the geometric stiffness matrix. Now, this accounts for the way that tensions can increase stiffness and compressions decrease stiffness. Now, you'll note that there can be some forces where the element and geometric stiffnesses cancel out. Now, this will cause the P delta analysis to fail, or non-convergence. Now, for buckling analysis, we're actually looking for those, and so you can see we've got a lambda times the geometric stiffness matrix. Now, this is a multiplier on the load which causes the collapse, and the deflection, the U, is then the buckling shape. And we use eigenvalue methods to find this. And similarly, we can use eigenvalue methods to take the stiffness and multiply on the mass matrix, the masses of the structure. These will then give us the natural frequencies and also the modal shapes. I also explore various non-linear methods, even down to things like meshless methods, not easy to say, but yeah, time is far too short to look at those at the moment. So you've done the model. Now, what about errors? Never forget errors. Hartford Civic Centre, Schleppner oil rig, CTV building Christchurch. These are just 3 structural collapses that are caused by bad finite element analysis. Thankfully, the first 2 had no casualties, but 150 people died in the 2011 Christchurch earthquake, all in that one building. We might add in the Florida University footbridge to this list, and so on. As I said earlier, all models are wrong, but some are useful. How can you make sure that your models are useful? So FEA, it stands for finite element analysis, but also finite element approximation. No digital computer can exactly represent real numbers. 3.14 is approximately pi. It may or may not be close enough depending on what you're calculating. Now, the maths of FE is to find a solution to a whole host of simultaneous equations. Now, if we were to find the intersection of two lines, then the answer is definite. Add in a third line, and the intersection becomes much more uncertain. So statically indeterminate structures are like this. They have this element of uncertainty about them. So how do we get the best answers from an FE model? There is validation. Validation is ensuring that the model is valid. Does it answer the right question in the right way? Is it realistic? Does it include important checks and details like voids or stability? Is the modeling appropriate? The Harvard Civic Center model was invalid because it ignored important details, such as the way as-built connections induced large amounts of torsion in members which had virtually no torsional capacity. Their analysis approach was also invalid as they did not check for torsional buckling. They did not ask the right questions. The CTV building analysis model was also invalid because they did check for seismic, but they only got center point story drift output. The building had an asymmetric stability system, so torsional drift was significant, and that's what led to collapse. We also have verification, which asks whether the model is giving the correct answers. Does it have errors in it? Now, one of the best ways to verify a model is to have a good idea what the right answers look like. Whether deflection, moment, shear. If the results do not match up with your expectations, then it's because of one of three reasons. One, your model is wrong. Two, your expectations are wrong. Or three, the software is wrong. And it is not normally number three in commercial software. The most likely answer is either you did not understand the structural behavior correctly or that you made an error in the model. Either way, it's time to dig in and find out where you went wrong. Now, hand calculations, great way to start. Even with a simpler model or assumptions, assume a truss is a beam or a tall building is a cantilever. Use beam theory to get approximate answers, or make simpler FE models and so on. Now, IStructE oil rig, that sank because a one-line beam shear force check was never done. So, apart from the errors, approximations inherent in modeling, where do the errors come from? Errors come in units. These are possibly the biggest cause in errors in models, at least the ones that I've seen across on my desk. Confusion between newtons and kilonewtons, or meters and millimeters, whether in the materials, the sections, the model dimensions, the loads. You can quickly find yourself out by a factor of 1,000 or even 1,000,000. If you overstraining the model can cause errors. I remember one case where the engineer put pinned restraints on the ends of all the beams rather than pinned releases. He then complained that the columns had zero load in them. Likewise, lack of restraints can lead to unstable models. Just because you do not have forces in a particular direction does not mean you don't need restraints in that direction. A zero stiffness will always stop the analysis, whether the model is a whole or in an unconnected element. Torsion is often forgotten about, as it sometimes can be crucial. So forgetting was the dominant factor in both the CTV and Harvard Civic Center disasters, amongst others. Inappropriate meshing, that will reduce accuracy, but it can be especially crucial on buckling analysis models, or dynamic models too. Meshing was also a factor in the IStructE oil rig. Keep halving the mesh until the results stabilize. Second order effects. If you've got large deflections, you need a non-linear analysis. And then you've got to remember, you cannot multiply or combine results from non-linear analyses. And there's also whatever else is that you've forgotten. Now, you have your model working well. It is time to make it work even better. Now, optimization is a thing, I think, that's almost all engineers are interested in, whether it's finding the lightest beam for making a bridge, lightest beam to making a bridge span several kilometers across sea carrying just its own weight. And now we also have the drive towards zero carbon construction, both from industry and from clients. I mean, the construction industry contributes about 8% of the world's greenhouse gases. The main emissions used to be from the service life of the buildings, heating or cooling, but improved insulation and efficiencies like that have greatly reduced those. Now it is the structure which is a major source of environmental damage, and we need to do our bit by making every building and structure more efficient. Now, I've heard many opinions as to what is optimization, and its simplest term, it is minimizing the cost of something in a design subject to various constraints. That the cost, the weight, the amount of material, the construction time, etc., etc. Now, here we have the standard formula, and I'm not quite sure if the standard formula are actually useful, but there seems to be a law that says all text on optimization must include this equation. So here they are. Now, we can put this another way. Optimization is finding the best solution out of the feasible solutions. But it's up to you to decide what the range of possible solutions is. Now, to computerize optimization, you need a cost function, a way of measuring just how optimum or efficient a solution is. And you need to decide on what variables you're going to explore or adjust to find that optimum. And you need to know what is and what is not acceptable. For example, a structure cannot fail, nor can it deflect too much. So you decided you got to minimize the cost or the weight or the structure time anyway, of your structure. How might you go about that? So there are three main categories of optimization. There is the section optimization, determine the best section size. And that is probably the simplest option. It also has the least effect on the overall cost of the building. There is the shape optimization, looks at the shape of the building, of the truss, of the section itself. And then there's the topology optimization, which looks at the scheme as a whole, span directions, number of columns, what materials you're using, and so on. Now, topology has the largest effect on the end result. So this is what you should do first. In fact, this list is actually in reverse order. But topology. So 2012, IStructE President John Nolan gave us, in his inaugural address, gave us a simple and powerful example of topology optimization. A simple single-story industrial building. Now, if we span the roofs in the short direction, is it best to have 2, 3, 4 bays? If we span the long direction, is it 4 to 9 bays? Do we put columns in everywhere or use hit and miss layout? Do we use moment bases to reduce the frame sizes but increase the cost of the foundations? I mean, even this, we are already dealing with over 100 different layout options. It's worthwhile exploring this, and then this will make big impact on the final structure. Or things like trusses. I mean, I've often wondered about over the years about the various forms of truss and which are the most efficient. Pratt, Warren, Fink, Howe. What I didn't realise was about 100 years ago, an Australian engineer called Mitchell had found the answer, and he used Maxwell's theorem of low paths, and he proved it is possible to determine the most optimum truss. And these are now known as Mitchell trusses, as you see here. And it's true that some have quite a lot of connections in them, which will push up their cost. But this does also mean that you can determine just how close your truss is to optimum. Now, to date, they've been mostly known to a few specialists, tall buildings, that sort of thing. But I would confidently expect that trusses such as one we see at the top here, we're going to be seeing a lot more of these in future. Now, topology and shape can often get confused. Indeed, the boundaries between the two can be fuzzy. So here are three examples. So here, the original form, And the topology remains the same if you can stretch one form into another without breaking it. Hence the often quoted example that a donut and a coffee mug are topologically the same, which could explain why they go so well together. Now, here the shape is a rectangle or a bowstring, while the topology is the number of internal elements in the truss. Now, shape optimization itself is getting the most from the structure by adjusting the location of the truss nodes, the section corners, the thicknesses, the ridge heights, and so on to get the most efficient structure. I-beams, generally recognized as being very efficient, but still they come in a variety of shapes, depending on whether they are being used for bending or mostly for compression or composite action. And shape optimization is essential if you're designing a compression or tension only structure, as the right shape should minimize the chance of buckling or wrinkles as is appropriate. And we have section optimization, which is something I think all engineers are familiar with, but can still throw up some problems. Optimizing the section for a single statically determinate beam is straightforward, but when the beam stiffnesses interact, then it gets a lot more complex. Even this simple cruciform of two beams, both with the same span, central point load, there are actually three principal optimum solutions. I mean, it's actually four more, seven in total, which I don't have time to cover now. And if you are looking at a more complex structure, such as a two-way spanning vierendal truss or space frame, then it takes a lot of iterations before you determine what the most effective set of sections are. Now, we do not have time to cover everything regarding optimization now. I've been known to talk about it for several hours, and this book contains 2 chapters on the subject. As a teaser, here is a list of the principal heuristics or methods for optimizing a structure or other engineering problem, all of which we cover. And now we go from looking at state-of-the-art to cutting edge, artificial intelligence and machine learning. Now, the concept of artificial intelligence has been with us since the dawn of the computer age. The term was invented in 1956 at the Dartmouth Research Project in the US, where a number of eminent scientists and mathematicians gathered together to make a machine simulate thought. The expectation there was if a carefully selected group of scientists worked together for a summer, then they should make significant progress. Now, 70 years later, we know they were rather optimistic, to say the least. But from a starting point, there were many useful techniques and methods that have arisen, even if none of them have come close to simulating thought. Now, the initial quest for artificial thinking was with symbolic logic or predicate calculus. Now, while they've completely failed to simulate thinking, the natural language processing did give us grammar checkers for our word processors. Very useful. Though by another technique, natural language processing is now found in most homes and pockets. So after machine learning parses speech sounds into words, NLP groups the words into sentences, works out which parts are nouns, verbs, adjectives from the grammatical rules, then determines the instruction or question, and then will either try to find the answer from the internet or play the music of your choice, or do something random. Search routines are AI. It's not possible to directly solve the question, what is the shortest route between 2 points? Instead, AI research produce algorithms such as A* and so on to intelligently search for the shortest route with a mixture of estimates, calculation, and data storage. Likewise, searching through unsorted databases is also an AI application, the most famous of which has become a verb, to Google. Another aim of AI is to encapsulate knowledge and enable automatic decision making, and this can be in the form of a state search. So state search builds a tree of possible decisions and then navigates it to find the best possible answer, or at least the most promising route to the answer. And these have proved very successful in games. Games like chess are formal, they have rules, and are boundaries. And while neural networks have been around since the 1960s, they were initially very unsuccessful. But now, with fast processors, powerful training algorithms, and the huge amount of data available on the internet, they are now the dominant machine learning method. Neural networks are inspired by how neurons in the brain connect together, collating data to enable pattern recognition. Artificial neural networks work by taking numerical data with a number of inputs, multiplying them, adding these together multiple times until an output indicates which is probably the answer. If they are right, those options are strengthened, and if they're wrong, they're weakened. And this neural network is then trained over thousands of iterations until it consistently, or at least generally, gives the right answers. Now, while machine learning methods such as deep learning have proved successful in applications such as recognizing videos of kittens on YouTube, in structural engineering, we have the problem of a lack of suitable data to train the systems. Hopefully this will change in future, and we will see more AI and machine learning engineering assistants in future helping us in our tasks. Now, computing has already made changes to the industry in my lifetime, and I foresee more of them coming. AI and machine learning will increase their presence. I think the major change to us will be due to climate change and the efforts to mitigate it. So the main thing that we must change is how much material we build. We must use less. We must also build less and refurbish more. Only doing new builds when there's not an option. Optimization is going to be a significant tool for us in the future, whether automatically exploring the structural topology, shape, or sections. And I know there's a fear that optimization could reduce factor safety, but I think hopefully we can see that improving topology and shape of the structures will improve efficiency without compromising any safety. There's also concern it might increase costs, which, yeah, in some circumstances it might be true, but by no means all. More efficient construction should be cheaper. There are also increased number of clients who want to ensure their projects are environmentally sound. And on the plus side, reducing the cost of structures will also mean more efforts, so should mean more fees. Similarly, refurbishment of structures requires back analysis of existing structures to work out what's actually there, and the searching for what is actually built from readings is another topic in computing. There are other technology advances we don't have time to discuss now. Mobile computing, it is there, it will increase its impact. I think many engineers over the last year without laptops and mobile phones will have really struggled to keep their businesses going. And also enabling me to talk to you half a world away. Cloud computing will reduce the need for local high-spec hardware, yeah, including more mobile computing. And then there's quantum computing, which promises much. We don't know yet whether it can deliver it or not, but quantum computing is far too weird to explore now at the end of this talk, but does get a section in the final chapter. So as I mentioned, I cover all these topics and more in computational engineering, and I'm very grateful that it has been very well received and attracted amazing reviews from around the world. And that point, so in the meantime, are there any questions?
I think it'll be great. Yeah, if anyone has questions, please just jump in. Otherwise, if you'd prefer to put in the chat, we can do that too. So any recommendation on applying stiffness modifiers in gravity load analysis? Most people reducing stiffness of slabs and beams for gravity loads analysis too. It doesn't make any sense to any recommendation on this.
Yes, so it's tricky. So I presume we're talking about concrete structures here. So concrete structures, the stiffness varies as the bending moment increases. In fact, I do have a couple of diagrams in the book on that, and the let me find that a minute. Let me see if I can find this. So the that right one. Yeah. So come on there. Right. Here we have the book. Nope. Where did I put it? No, let me just jump to about there. Nope, come on. Why is it not? Oh, there we go. Yes. Right. Nope, that didn't work. Okay, so concrete stiffness, cracked section stiffness. When the bending moments are very low, you see it's got quite a high stiffness. Then as the bending moments increase, you get cracking and then a gradually reduction in stiffness. So the stiffness is a function of the bending moments. So without this information, you can take a quick guesstimate and go, it's about half, um, or some other value, or so. Sorry, there is the short-term crack section stiffness with maximum rebar to long-term crack section stiffness, minimum max rebar typically. And so yeah, stiffness does reduce with moments. Are you just guessing, or are you actually working out what those stiffnesses are? A more accurate stiffness will give you a more accurate deflection. So yeah, it can be done. It's yeah, it's in your hands.
Cool. So thank you. Next question. They're filling up now. So we have a question. What are the strengths of robot structural analysis?
Robots.
Can you yeah.
Oh, you don't want to use robots. You
Yeah,
want to
we
you want to use
GSA.
GSA. Yeah, I would GSA. It's the Iffy analysis program produced by Arup. So it's produced with um, um, decades of um, engineering experience behind it. And I've been working with it on it for over 15 years now, so I can say the support system is very, very good. If you have your question on GSA, you will get an answer from a qualified engineer, and it's we're constant development. It's always in being improved. So yeah, I love it. It's
I can back you on that one. I do love using GSA, and can vouch for how amazing it is.
but if you want to explore it in more detail, drop me a line and we can arrange a more detailed chat.
Okay, next question. Any dynamic modeling examples in the book?
Yes, do cover whole section on well, dynamic analysis. Yeah, so go into the dynamic analysis, what's uh, what's involved with it, plus some discussion on the modeling requirements for modeling for vibration, as we can see here.
Great. And then next question, when deciding on the mesh size for an RC slab in an Iffy analysis, what factors must one consider?
Okay, which also is in here somewhere, possibly under the meshing section. Mesh size. So first of all, there is a minimum mesh size, and the rule of thumb for the minimum mesh size is twice the thickness. Within that, yeah, you're getting to deep beam theory and the analogies break down. Larger mesh size is yeah, if you make mesh too big, the results are too crude. So generally, you're looking at breaking the spans down into about 10 nodes to get good beam moments in a mesh. Now, ironically speaking, if you've got a span to depth ratio of 20, then the 10 elements versus twice the element thickness actually gives you the same dimension. Other things to watch out for around column connections. The real flat slab column connection is a slab with a thickness and a column with dimensions, where you're modeling 1D elements and 2D elements, which are literally one-dimensional, two-dimensional. It's a pin supporting paper. If the mesh size, so you have a what we call a singularity at that point. As you reduce the mesh size over the column support, the moments keep going up, and an infinitely small mesh will give you an infinitely high moments. Now, reality is you don't get the moments, or the moments just level off within the connection size. So basically, there's no point even meshing within the connection itself if you do restraints, or stop the meshing once it gets to that point. So there are things to watch out for there. Likewise, also buckling and dynamics, which I cover in here somewhere. Maybe it's not. It's in the errors section, isn't it? Step where is it? Yeah, so the buckling and dynamic analyses, you will find as the mesh size reduces, the results will change and they will usually level off. So you've got to make sure that you mesh fine enough to actually get the results you're looking for. And the general rule, keep halving the mesh size until the results don't improve anymore, or you hit the twice thickness limit, and that's probably close enough.
Okay, thank you. Next question. Can you please give advice on where someone can start to apply computational methods in standard structural engineering practice? Some ideas that could be easily implemented in everyday work and standard projects. And also, are there any such examples in the book?
Yeah, it's the book is full of all sorts of ideas. Yeah, how to apply good modeling, and all the approaches you do to making a model which is useful, but also some of the quantitative checks you can do about qualitative understanding of the structure, but also about in here somewhere about creating models which are sufficiently similar. So I've got a few sort of standard beam theories and so on. You can use some measurement trusses. If it's a truss, WO squared upon 8 divided by the height. And you should know also if it's a cable or if it's an arch, also here somewhere. The arches, there we go. Formula here for arch, WL squared upon H, WL squared upon 8H. Yeah, there are lots of whole range of suggestions in here and things that you can do.
Awesome. Next question. Are piles or piled rafts considered in the book? And also, where can they find more info on the project's examples you mentioned where regarding the failures, where the computation errors caused failures?
Yeah, so I don't get too much into the geotechnical. I do talk about there is the soil structure interaction part, which I can't remember where that is. No, in here somewhere. Actually, it's the same as the where was it? Oh, sorry. Yeah. There we go. Yes. So yeah, I do talk about source structure interaction a bit. Don't get into piled rafts as such. It's getting much more into the geotechnical side, but yeah, again, I've got a presentation separately on pile draft analysis, and I can send you the link for that. The sources for the various disasters, I do talk about the problems directly in in the text and some of the things which went wrong, but also there is the extensive references at the end, which then links through to the various papers and so on, that relates to those disasters. Good reading, very important to avoid those in future.
Great. Back to the mesh
Mhm.
sizing. Are there any consequences of using too small a mesh size, if any?
Yeah, so the consequence of too small mesh size, it, there's the unrealistic moments at supports. There is the running time. You make the mesh too small, there's, you halve the size of the mesh, you've got 4 times as many elements in and more runtime. Also, a point where the accuracy goes away. Yeah, those are the main things. Also, of course, at the connections, column to wall, slab to wall, column to column, beam to column, and so on. Make the mesh size too small. The results, you don't really gain anything from the results. So that's the main thing. Time and the occasional inaccuracy.
A question from Jonathan. How do you envisage the role/daily tasks of structural engineers evolving in the next 10 to 20 years? What value or benefit will human intelligence bring in an increasingly computer-dominated world?
Well, yeah, I think the main thing is that computers, they are really good at doing the maths, and we should let them do the maths. Now, when I used to do design projects, the portal frame, for example, we would go, well, we're gonna make it this span, that these are the various spans and everything. We just make it work. That's the scheme. We just go for it. We just do one scheme, do the calculations. That's the answer. Likewise, concrete sections, rules of thumb, how deep is it going to be, how wide is it going to be, work out what reinforcement you need. Now the computer can just run through all the various options and give us the better answer. But also, I foresee the AI type things maybe acting a bit like the assistants, that it can maybe make suggestions, maybe do some exploration, but gives us then more time to be creative. If you think about what the options are, what can we do? And some of the read something like that work by Peter Rice and so on. They're creating some very efficient structures, but they're very non-linear. Non-linear analysis is we can't it's very difficult to do by hand. And so the computation enables us to do those sort of structures and those efficiencies. Likewise, or the parametric designs that we're getting now. Difficult to do by hand. So it's computing have always been forecast to give us more leisure time. I think more creative time. I think, and let it do the mechanical things, and we can do the get more involved in the design of the structures, design the buildings, design the bridges. Don't let the architects do everything. We're not just there to size beams for them.
Get the creativity
Yeah,
going.
definitely.
A knock-on question to that is, do you see this as a topic for formal education for future engineers at, say, university level or postgrad?
It definitely a postgrad. I've been working with University of Bradford to put together a course for computing, a computing and structural engineering course at Bradford. I know there are postgraduate courses in places like the Netherlands and so on. Undergraduate, it's a bit tricky because undergraduate courses are so jam-packed with basic theory, which we probably still need. We always need basic theory. It's very difficult to squeeze something into an undergraduate course without taking something else out. I mean, maybe we'll see more structural engineering degrees rather than just civil engineering degrees. I don't know. A structural engineering degree would allow more space to do more computing, and certainly some computing is definitely necessary at undergraduate level. Otherwise, you come out of university with no knowledge and you're just doing hand calculations. I have done FE courses where the students asked, do they need to do the FE calculations by hand? Thinking, no. No. You don't. You might do that as an example to learn what the computer's doing, but after that, let the computer get on with it. But I think mostly at postgraduate level, once you know this is the career route I'm going down, this is what my interests are, then sort of delve into that detail more.
I'm aware we're on time, we're over
Cool.
time, but I think this is a good question, so maybe we can fit in this last one.
Okay.
Are there any recommendations on designing slabs using FE model versus yield line theory?
Yeah. I don't know. Because yield line theory gives very different results to FE analysis. And I do know I don't know of any program which can do both. I know obviously FE programs do FE analysis. I've seen some standalone yield line theory programs. To be honest, most designs you should probably do the design or analysis two ways anyway. So even if you're doing an FE analysis, I would probably do a yield line analysis on the side just to make sure they're giving similar results. How appropriate yield line analysis is, how valid it is, something I have doubts about, but I'm not qualified to state anything. A lot of people are very keen on it, and I'm sure they know what they're talking about.
Awesome. So thank you so much, Peter, for today. I know it wasn't an easy challenge squashing this whole book into 45 minutes,
It
so
was a
thank you so much.
95% reduction.
It certainly has inspired me to dive into the book and find out more about these different topics. So thank you so much. And thank you everyone for joining today. I hope you've enjoyed it, and yeah, enjoy the rest of the afternoon. Thank you.
Thank you much.
Cheers.
Bye.
Bye.
Bye.